Section 2.2, Instantaneous Velocity and Speed. Let's take a look here. So instantaneous velocity is what is often just referred to as velocity, v. So if we haven't specified, then the default is instantaneous velocity. It's at a single moment or instant in time, and it's obtained from the average velocity by shrinking our delta t down. By shrinking our time interval down, we can look at the limit as that time interval approaches 0. And as we get to smaller and smaller time intervals, our average velocity becomes more and more instantaneous, right, to a single moment. The velocity is given by the slope of the position time curve for a particle at one instant, or in other words, the derivative of position. So this is connecting back to calculus that you've seen. The derivative of position with respect to time gives you velocity. It's all interconnected. Now calculus finally makes sense. It's in its proper context, physics, because physics rocks. Anyways, velocity is a vector quantity with the same units as average velocity of distance over time, or meters per second. That's our SI unit for it. And the sign of the velocity will represent its direction, because we remember vector quantities need to have a direction. So the sign of the velocity does matter here. So we can write our velocity is the limit that our average velocity has its time interval go down to 0. Or more succinctly, we can write it with this dx dt, the first derivative of position with respect to time. That's the way I like to write it. Now speed is the magnitude of the instantaneous velocity. So again, if you just hear speed referenced, it's assumed that it's referring to the instantaneous velocity. So a velocity of 5 meters per second versus a velocity of -5 meters per second both have the same speed of 5 meters per second, right? It doesn't matter which way you're going on the highway, the police officer will know exactly how fast you're going. So if you're going the wrong way on the highway, you might get a ticket for another reason too. Anyways, let's take a look at an example of this. So here's a graph that shows the position of an elevator as a function of time. So we have position on the vertical scale here, and then time on the horizontal scale. And so this can be a little bit abstract to picture, but notice the position starts at 0 and stays at 0 for a while. So this is the elevator's just chilling, right? And then the position starts to change. So that means the elevator needs to be moving now. And then sure enough, the position stops changing as time passes. The elevator again is stationary. And the way that we can get that is, besides just imagining an elevator, which is good practice, is we can look at the slope of the position as a function of time, right? So at the very beginning at point A and the very end at point D, it's a flat line. So the slope there is 0. That means the velocity is 0. It's not moving. In this middle section, it's moving at a constant slope. We have a straight line there. So when we take the derivative of this part of the line, we'd have a constant value, that its velocity has a constant value. And then there's a region from A to B where we notice it's like it starts out, I'll get a slightly different color here. It starts out with no velocity, and then that slope starts to increase, right? We go from having 0 velocity to a larger and larger slope, which means that we are now speeding up. Similarly, from C to D, we start out with a large slope, but as we get to that shoulder, that slope actually levels off and we get a smaller and smaller value. So if we want to plot this, which is a really good practice, then we would pay attention first off to the easy points where we have a constant slope, because that's going to be simplest, right? So at point A and point D, the slope is 0, it's flat, and so sure enough, the velocity is 0 there, right? That fills in very nicely. And then from B to C, where we have the straight line diagonal, that's also a constant slope, so the velocity has a constant value of 4 meters per second. And then the intermediate regions are the harder ones, right? That's where it's constantly changing value of velocity. So the velocity starts out at 0 and increases until it gets to 4, And similarly, starts out at 4 and decreases until it gets back down to 0. So this is a different way of thinking, to have this graphical experience. Some of you may have a lot of experience with this from your calculus class, depending on your background. Others maybe not as much. But I'd encourage you to get comfortable with it, to try and practice as much as possible. And on that note, I have an opportunity for you to practice it. So this is a think, pair, share. Which velocity versus time graph goes with the position versus time graph on the right? So I want you to take a moment to reflect on this. Choose an answer, even if you have to guess at random, but write something down and say, this is my answer. And then you can go ahead and play the video and go on. So go ahead and hit pause now. All right, hoping you did that. So as we're thinking about this, we know position versus time. To get to velocity versus time, we're going to pay attention to the slope of the position versus time. So my favorite method here is to look at the most obvious slopes. So the easiest slopes for me to find are where it's about 0. So at the end here, the slope is 0. That tells me my velocity is going to have to be 0 at the end of this time interval. So the velocity graph is going to have to intersect with 0. And there's only 2 graphs that do that. Notice this other one, B and A, both have these positive large velocities at the end. They're flat, they look similar to the position versus time graph, but they aren't showing a velocity of 0. So that really helps, because now we've ruled out those 2 and we just have C and D to decide between. So then we can look at this first part and notice that we have a constant slope. And notice both of these have a constant value of velocity as well that matches that constant slope. The thing we have to pay attention to is this constant slope positive or negative? And it is going in the positive direction. It's a positive slope, as opposed to a negative slope would be if it was going downward. So because it's a positive slope, that tells us we have a positive velocity versus a negative velocity. And so with that in mind, it's going to have to be graph C that matches this graph of position versus time. So sure enough, that is what the answer comes out to. So if you didn't get C, or if you did get C but for the wrong reason, I encourage you to spend more time with this. Look for other examples. Chat with me in office hours or on the discussion board. You can chat with other people too, but spend some time ironing this out, because once you get it, you feel a whole lot better. So encourage you to keep pushing through.